Wouldn't it be nice to fly from Tokyo to LA in 2 hours instead of 10? Such a fast trip seems like one of those futuristic dreams our great-grandparents naively expected to come true by now. The Concorde introduced supersonic flight in the 1970s, but that jet flew just twice the speed of sound. The idea of hypersonic flight, which is much faster, has been around since the 1930s and has been researched since the 40s. But 80 years later, flying across the world still means a full day in a tiny seat, jockeying for the armrest. So what's stopping us from building a plane that can go really fast? As it turns out, part of the problem is making it also go slow. By traversing the Atlantic Ocean at around Mach 2, the Concorde could fly from London to New York in just 3 hours. What's a Mach, you say? I'm glad you asked. The Mach scale tells us how fast something is traveling relative to the speed of sound for the material that something is traveling through. The speed of sound, meanwhile, relates to how fast all the particles that make up the material can bump into each other and transmit a wave of energy. Traveling at exactly the speed of sound is equivalent to a Mach number of 1. A Concorde flying at Mach 2 is moving at twice the speed of sound, and so on. Anything that moves faster than the speed of sound is said to be supersonic. The Mach scale is useful because the speed of sound varies not just for different materials, but also the same material under different environmental conditions. In the case of a plane flying through air, the speed of sound changes depending on the ambient temperature and altitude. Two planes could be going at the same speed in terms of kilometers per hour, but have different Mach numbers if they're moving through different parts of the atmosphere. And unlike measurements like kilometers per hour, which just tells you a speed, the Mach number will always give you a good idea of how much the material is being compressed or shoved out of the way. This leads us nicely into one reason you can't fly on a Concorde anymore: sonic booms. At supersonic speeds, the air a plane is flying through can't get out of the way fast enough. Instead, it gets compressed into a dense cone that's powerful enough to break windows and damage eardrums. So the Concorde was super noisy on account of the continuous shock waves following in its wake. Maybe some people would be willing to tolerate that for a shorter skip across the pond, but it was also so expensive to develop and operate that the company never turned a profit. It closed up shop in 2003. But we aren't here to talk about mere supersonic flight. We're here to talk about hypersonic flight. Flights exceeding Mach 5. Hypersonic travel has the clear benefit of being faster, but at high altitudes, it also creates less atmospheric turbulence. And yes, this isn't just a perk for people looking for shorter vacation commutes. As you might imagine, there's a lot of military interest in tech like this. But let's stick to the physics of it all. How fast could a plane possibly fly, and what's stopping us from getting there? First, some aviation fundamentals. If you want your vehicle to be a plane, you've got to balance 4 forces: propulsion, drag, gravity, and lift. Propulsion is the force that pushes a plane forward. It's generated by an engine that accelerates a mixture of air and fuel backward, creating an equal and opposite push forward in response. Thanks, Newton's third law of motion. Meanwhile, drag is the force that slows stuff down as it moves through a fluid. It comes from a bunch of different sources, like the friction between air molecules and a surface, and the fact that an object moving through fluid has to constantly expend energy, pushing some of that fluid out of the way. But if you're traveling faster than sound, there are even more sources of drag, both inside your vehicle's engines and created by the sonic boom causing pressure cone you're leaving in your wake. So drag is a big deal for any plane, but even more complicated at super and hypersonic speeds. Next up is our old friend, gravity. The amount of gravitational pull depends on the mass of the plane, which is constantly changing as its engines burn fuel. And finally, there's lift, the upward force that keeps a plane in the sky, and it's why airplanes need wings. I'm gonna be honest, lift is really complicated, and aerodynamicists are still arguing over the various effects that contribute to it and how much each effect matters, so I can't give you a perfect definition of lift, but here's what you definitely need to know. The shape of a wing creates a difference in pressure between the top and the bottom sides. A well-designed wing will create a low pressure zone on the top and a high pressure zone on the bottom. More pressure on the bottom results in a net upward force. At the same time, as air flows over both sides of the wing, that wing also pushes some air downward. It changes the air's direction by exerting a force, and as the wing pushes down on the air pushes back up on the wing, contributing another pure source of upward lift. Thanks again, Newton's third law of motion! Tweaking the interplay of these four forces, propulsion, drag, gravity, and lift, is the prime directive for any aerospace engineer. So how far can those engineers push these principles to reach faster speeds? Before we jet off to jets, we have to pay the bills, so here's a quick ad. This SciShow video is supported by JUMP. Most of the stuff we talk about in SciShow videos comes from academia, where researchers collect the data we're going over right now. But none of those people know what their data means until they analyze it. That's where JUMP comes in. Plus, teachers can use JUMP as a pedagogical partner in your classroom. Its visual and interactive approach to data analysis helps students grasp complex statistical concepts and more easily discover insights in their data, which is why more than 1,300 colleges and universities around the world use JUMP. All students, educators, and academic researchers at degree-granting institutions get a full-featured version of JUMP for free. But you don't have to be an academic to get JUMP for free for 30 days. Just go to jmp.com/scishow. Every flight starts by taking off. To get a plane up to altitude, you need lift and propulsion. Wings are designed to do most of the heavy lifting. The shape and area of a wing determines just how much lift it can provide. Now, fluid dynamics is so complicated, it's both really hard and unreliable to calculate the lift factor for a wing. Plus, like Mach numbers, a lift factor also varies as the density of air changes. So usually it's just measured experimentally. The amount of lift a plane can get also depends on its velocity. At hypersonic speeds, this matters a lot more than the wing shape does. And velocity depends on both the amount of propulsion you can create and how efficiently you can reduce drag. So although we're currently concerned with lift, we simultaneously have to figure out how to streamline the plane so it can plow through the not-so-thin air. One goal is to make the plane as smooth as possible to avoid stirring up the boundary layer. That's the relatively calm layer of air directly in contact with the plane, which acts as a buffer between the plane and the hypersonic airflow around it. Sharp corners or other disturbances in the boundary layer can create zones with high pressures and temperatures that fluctuate incredibly fast. Any kind of unpredictability or turbulence equals new sources of drag, so in general, sharp corners equals bad. Because of this, most hypersonic vehicles have sleek shapes and do everything possible to reduce their volume and cross-sectional area. And with such a slender shape, you have to get pretty clever if you want to carry a lot of stuff. But really, a plane like this shouldn't carry much stuff, because the more it carries, the heavier it is, and the more fuel it needs to defy gravity, which makes it even heavier, which means it needs more fuel, and so on. For something large like the space shuttle, you can use rocket boosters to get it to its target elevation, which, as the name suggests, is above most of Earth's air. So despite the wings sticking out of its belly, the shuttle didn't really operate like a hypersonic plane most of the time. Smaller vehicles can also be ferried by a carrier plane and then dropped. Once they detach, they accelerate with boosters or special hypersonic engines. While those engines are pretty tricky to design, they're more all-purpose than rocket boosters. Rockets might be way better at getting a vehicle up to cruising altitude and speed, but they burn fuel to accelerate and have to carry all of their fuel components with them. Engines, on the other hand, use fuel to accelerate the air itself and produce thrust. So they require less fuel when cruising. And compared to some rockets, they have more flexibility concerning when they turn off. Speaking of fuel, there's another thing to consider here. Current fuels are, well, not exactly good for the environment, so maybe you can make something go very fast, but someone has to decide if it's worth the economic and environmental costs. But getting in the air and up to speed is only about half the problem. Once you're cruising at Mach 5, you'll have a different set of worries. At hypersonic speeds, weird stuff starts happening to air. For one thing, some of its molecules start to break apart when the plane plows through it. This means that the temperature of the air can vary by a lot, even in a pretty small volume of space. Remember, lift depends on air density, and air density depends on temperature. You might not think it, what with the altitude and all, but hypersonic vehicles can get very hot. Their thermal coatings have to be able to withstand temperatures up to 2,000 degrees Celsius. So yeah, if you're looking to transport people, you'll need shielding that keeps them from roasting in their hypersonic tin can as it hurtles through the sky. Another weird thing that happens at hypersonic speed is that the wings, the things that make the planes, become a structural liability. But reinforcing the wings to keep your plane from getting torn asunder means adding more weight for the lift to counteract. This is why the few hypersonic vehicles that have been designed don't look very plane-like, from the previously mentioned space shuttle to 3 experimental X-43As, which had neither pilots nor passengers nor landing gear. Each intentionally crashed into the Pacific at the end of their first and only flight, never to be recovered. As it turns out, it's one thing to design a plane that flies at hypersonic speeds. It's another thing entirely to design a plane that can take off and land at reasonable speeds while also flying hypersonic in the middle. Since booster rockets aren't ready for commercial use yet, you'd probably want to rely on some kind of hypersonic engine. But engines that work above Mach 5 don't work so well under Mach 1 and vice versa. Realistically, you're looking for an engine system that dynamically switches modes, which would be incredibly costly and time-consuming to develop. And if you want to carry people, safety is an absolute must. So you'll also need sophisticated control over the plane's acceleration, cabin temperature, and vibrations, just to name a few. In other words, hypersonic technology has a long way to go before anyone starts recruiting flight attendants, even if there are humans who have flown in hypersonic planes. Like back in 1967, an American pilot pushed the X-15 all the way to Mach 6.7. First, he was brought to a high altitude by a carrier plane. After they separated, he ignited the X-15's rockets and accelerated to more than 7,000 kilometers an hour. Meanwhile, uncrewed hypersonic vehicles have been used for military purposes for years. Obviously, a lot of the details are classified, but engineers seem to be making some pretty significant advances. In 2021, China flew a prototype plane over the Gobi Desert and managed to reach Mach 6.5. Everything stayed pretty hush-hush until late 2024 when full press reports came out. It isn't clear how or even if their plane overcame the hurdle of operating at both slow speeds and hypersonic speeds, but this is a particularly interesting test flight because the shape of the vehicle is round and broad. That sure sounds more passenger-friendly, but there's a reason why your classic hypersonic planes are the opposite. A sleek and slim shape prevents a high-pressure zone from forming on top of the vehicle, which pushes down on the plane. Not exactly helpful when you're trying to keep a plane up in the air. China's prototype throws this philosophy out the window. Its broad cone shape creates that undesirable high pressure zone, but it also diverts that pressure over the body and into the wings that sit atop the vehicle. The diverted air pushes up on the wings, which push back down on the air, converting the pressure into upward lift. A third and final thanks to Newton's third law of motion. With far more room inside the vehicle and repositioned wings to compensate, it's truly a fascinating design. And it could be the breakthrough aerospace engineers have been waiting for. But in the end, most of the challenges with commercializing hypersonic flight will probably have to do with economics. Supply, demand, cost, and so forth. Some company may eventually announce the Concorde 2.0, but you can be pretty sure it won't come at basic economy prices.